Lesson 8702, Combining Exponents, Equivalent Expressions with Exponents. In this lesson, we'll identify equivalent expressions and write equivalent expressions involving the product of powers and powers of powers. Okay, hopefully we've worked through the lesson on Desmos, or the activity on Desmos. We're on page 113 to kind of nail down some of the things that we saw in that lesson. There's two learning goals today. The first one is to describe what it means. For two expressions with exponents to be equivalent. Running out of room there. And the second is just to create equivalent expressions with exponents. That's going to be a little harder. Okay, so sometimes writing an expression in an equivalent way can help us compare it to other expressions. The fact that exponents represent repeated multiplication can help us to write equivalent expressions. Now, equivalent expressions just mean that the evaluated value of the expression is equal. Now, we're going to lean pretty hard on expanding things out to see if things are equivalent. I think it's going to make a lot more sense to do that. So when in doubt, expand it out. We're going to look at some patterns and talk about some rules that we used in the activity. But when in doubt, writing out all of the factors might help you to see things more clearly. So we're going to decide if expression 1 is equivalent in value to expression 2 for each of these pairs. And this is a good tip. Consider expanding each expression, just like they did in this first example. Now, as we're going, I'm just going to point out the three different rules that we talked about in the lesson during class. And those are going to be some things that might be helpful to put on a note card later on. All right, so let's look at this first pair. Expression 1 has 12 to the second power, and that is raised to the third power. Let me highlight a few things here. So this is what's being raised to the third power. So everything in yellow there is being multiplied by itself 1, 2, 3 times. So here's the first time. That 12 squared is 12 times 12. Here's the second of 3 times. There's 12 times 12 again. And here's the third of 3 times. That's 12 times 12 again. And when we expand it out like this, we can see that 12 appears as a factor 6 times. I'm just going to write 12 to the 6th power here. But expanding it out is really what helps me to see what's going on. And this was the first of 3 patterns that we saw in the activity today. It's when we have a power raised to another power. I'm going to write power raised to a power. And the rule for how we get from these exponents to this exponent is we're really multiplying these exponents together. And that gives us the 6. And the base stays the same. Now you can either try to remember that rule or write it on a note card, or you can rely on just expanding it out whenever you see a power raised to a power. Either will work. So we're going to see if this expression is equivalent to this expression. This really represents the second of three rules that we talked about, or three patterns that we talked about in class today. And it's when we're multiplying powers that have the same base. There's a pattern that we'll see there. I'm going to write powers with the same base. When we have two powers that have the same base, let's look at what happens with the exponents. The exponent tells me how many times the base appears as a factor. So 12 to the fourth power means that I'm going to have 1, 2, 3, 4 factors of 12. And 12 to the second power means I'm going to have 1, 2 more. So in total, I have 1, 2, 3, 4, 5, 6 factors of 12. And I'm really adding these exponents to get the total number of factors. And again, I have 12 to the sixth power. And that's where the 6 really comes from. So in both cases, I have 6 factors of 12, or 12 to the sixth power. So these are equivalent expressions. So those are two of the patterns that we saw in the activity today. This represents the third one. Let me get another color here. Let me do purple. So in this case, the bases are different, but the powers are the same. So this is our third pattern, powers with the same exponent. So let's look at what happens here. I have 7 to the third power and 2 to the third power. When those exponents are the same, I'm going to expand out this first one. That's 7 times 7 times 7. And I'm going to expand out this second expression, 2 times 2 times 2. And because I have the same number of each factor, I can pair those together. So I can rewrite this as 7 times 2 times 7 times 2 times 7 times 2. I still have a 7 3 times and a 2 3 times as factors, but I can kind of group those together. I could even call that 14 to the third power. Or I can do 7 times 2 to the third power like it shows right here. So when I have powers with the same exponent, I can multiply the bases. And that exponent stays the same. 7 times 2 is 14, and I keep that exponent of 3. So, like we just said, 7 times 2 appears 3 times as a pair, and that's really what I have here as well. I could simplify what's in the parentheses, and these are equivalent expressions. So these are the three patterns that we saw in the activity today, and we'll get more practice with them in lessons to come. Let's look at the remaining couple of pairs to see if they're equivalent. The first thing we should notice in this column is that I kind of have some repeated multiplication, but these plus signs really throw a wrench in that. So this ends up being 16 times 16 times 16, but it's plus 16 to the second power plus 16 at the end there. So I expanded out what I could, but those plus signs are real speed bumps into the flow here. This isn't the same as 16 to the sixth power. If I expand that out, 16 appears as an uninterrupted factor 6 times. 1, 2, 3, 4, 5, 6. So here I have plus signs interrupting things, and here it's all multiplication. Those would come out very differently if I calculated those out. They're not equivalent. And then finally, this is going to be a little leggy, but I'm going to expand things out again. If I have 15 to the 6th power, I'll expand that out. 15 times 15 times 15 times 15 times 15 times 15. So 15 appears as a factor 6 times. Now, at first glance, it doesn't even look like this has anything to do with that one. The exponents aren't the same, the base isn't the same, but I do have a couple of 5 times 3s. There's a 15, there's a 15. Let's see how many I actually have if I raise this to the 4th power, which means I'm going to just write all of that out 4 times. This is where it's going to get a little bit leggy, but stay with me. So let's start with the first time. We have 5 times 3 times 3 times 5. Right, that's once. Times 5 times 3 times 3 times 5. That's the second time. I'm going to keep going 2 more times. 5 times 3 times 3 times 5. And then the last time. 5 times 3 times 3 times 5. Let me see if I can just help us see that. There's 1, there's 2, there's 3, and there's 4. Okay, so I've raised this yellow stuff to the 4th power. Let's see how many 15s I really have there. That's a 15. That's a 15. All of these pairings of 5 and 3 as factors means I have another 15 as a factor. Okay, I'm supposed to have 6 of them. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so those are not equivalent. It's a little buggy, but expanding it out is going to help us to see